How do you design, build, and fly 3D printed drones? That's what we're covering in this podcast episode. And to do that, we're joined by two special guests who, over the past 2 years, have done exactly that. Santiago and Mateo, thank you for joining me on this episode.
Hello, thank you for having us.
Hello, thank you.
So first of all, over the past couple of years, you've designed and built two UAVs that are 3D printed and have impressive flight characteristics. What are these two different types you've printed?
Okay, so they're not fully 3D printed. They combine a mixture of different manufacturing techniques, but as you can see them on screen,
Yep.
we'd like to talk about them like more in detail, like along the video, along the podcast. So what would you like to start knowing?
Well, first of all, you told me that there was a project that this was designed for, both of these ones. What was that project about?
Okay, so this was for a competition called DBF, organized by the AIAA, which is
Yep.
done every year. I don't know if Mateo would like to.
Yeah, this is a university competition, so everyone, any university around the world can participate. There are a lot of universities like MIT, Purdue, us from Colombia, from Universidad de Antioquia. There are a lot, so it's a great experience that you as a student can have because
Yep.
you learn a lot, not only about designing aircraft, but all about time management, resource management, and all the things that you need to fully create an aircraft and be successful in the competition.
Okay. And you're in the team, both of you, for the last 2 years?
Yeah, correct.
Yeah.
Mateo was the team lead, and I was the aero lead on both occasions.
Okay.
Mhm.
And how did it go those 2 years?
Great. I mean, our first experience was in 2024. It was the
Yep.
aircraft that you see on the left. So that aircraft was called Dumbo because we went with a canard configuration that is pretty particular. It's not
Yep.
a conventional configuration that you see often. So it was our first participation in our university. And we did good. Out of 107 universities around the world, we placed 21st, yeah,
Okay. Well, that's good.
in the competition. Yeah, it was good.
Especially because our undergrad is completely new in our country, so everything was like super brand new.
Yeah. So sorry, go ahead. This Dumbo, you can fold the wings up, the canards and the wings, is that right?
Yeah, correct. That was one of the requirements for the competition, that the aircraft had to fit in a space, in a certain space. I don't remember exactly
Yep.
the space. It was like 60 centimeters. Mateo, you remember?
Yeah, I think it was 60.
Yeah, like 60 centimeters. So the aircraft had to fold the wings. That was one of the requirements. The other requirement for this plane was a very short takeoff. The maximum was like 6 meters, 20 feet, something like that.
Okay. And what did your plane get up in?
Oof, I don't know, like 30 centimeters.
Yeah,
Okay.
I mean,
Well,
that was also something funny to experience because at that time we only have flown in our country that it's very high. It's like 2,600 meters.
yep.
So it was pretty high, and the air density changed a lot.
Yep.
Because that was that when we flew in the competition, it was in Wichita. That
Okay.
it was like 50 meters above sea level, so the
Yep.
density changed a lot, and maybe that was something that we didn't account for because we underestimate the
Yep.
capabilities of our aircraft.
Yep.
Yeah, that's the thing.
Th-
hmm
That's better than overestimating it, so at least it still got up in the air.
Yeah. You have to manage like your limits. That's the thing that you have to do testing, right? You need
Yep.
to understand the limit of your aircraft. Yeah.
So,
We also have like
sorry, go ahead.
limits on the testing that we could do because, like Mateo said, the altitude and also the terrain because the airstrip was like a bumpy grass strips.
Yeah,
Yeah, it wasn't comparable like the conditions that we could
Mm-hmm.
yeah.
compare it with.
So you designed it for a much harder set of requirements, and
Exactly. Yeah.
at 2,600 meters, how did the air density and takeoff distance differ to Wichita?
In our country, we
Yep.
did like the maximum that we could. That was like 6 feet. No, sorry,
Okay.
20 feet. 20 feet, right, Santi?
Yeah, the maximum for the competition was 20, but I think we didn't manage to take off at that distance in here. I don't think so.
It was like something above that. It was near. Yeah, yeah, yeah. So we did like, oh, okay, we can lower our payload and and we will be good to go.
Okay.
And then we go to the competition and take off in 30 centimeters. So yeah,
Yeah. Well, that's impressive. That's almost VTOL.
yeah.
That's a very important point almost because VTOL wasn't allowed.
Okay.
Yeah.
So,
Uh-huh.
how did you manage to get up in 30 centimeters? What parts of this design on the left allowed you to get up that quickly?
Well, definitely the tilting rotors. As you can see, I don't know. I'm gonna start jumping ahead
Yep.
on these slides to show you,
Yep.
like here. The
Okay.
tilt.
Yep.
Yeah, that's the thing. In the competition, they did say you cannot do a vertical takeoff aircraft.
Yep.
But they didn't say anything about tilting your rudders.
Yeah.
So yeah, it was the
So
first
you-
time that someone, I mean, any university presents something like that. So you have to go through a tech inspection before
Yep.
doing your missions in the competition. So it was like a delay on our aircraft because they were looking at the rules and saying, yeah, maybe this could go. No, yeah.
Okay. And the two rotors, there are two rotors I can see, is that right? For these tilt ones?
Yeah, that's correct.
How did you balance the plane while it was taking off then?
Because that's one of the points. We don't have a full VTOL.
Yep.
We need certain like horizontal speed, so that's
Yep.
enough to have control on the control surfaces.
Yeah. So by that you mean with the canards you need enough forward speed to be able to produce enough lift to balance out any pitching moments.
Yeah, exactly. Yeah.
Yeah, that's the other thing. Yeah, because we have different options for the canard. So we can have, for example, a fixed one that you can only have like new control surfaces added. But as we know, we needed a more dynamic pressure, right?
Yep.
But if you can have that velocity to increase that dynamic pressure, so you need more area. And
Yeah,
basically what we
yeah.
did is go full tilting canard too.
Okay.
Yeah,
Yeah.
it's another no flying canard because as Mateo said, if we were the other route, like using a conventional elevator type of control, then the downforce of the elevator would like hinder the
Yep.
takeoff capabilities. Or that was what we thought at the moment.
Yeah. So that's an interesting point because with canards, this is a distinction that a lot of people don't think about or talk about or learn about much. With the conventional setup with a regular plane where you have a horizontal stabilizer at the back, that horizontal part is producing downforce to actually balance the plane. With canards, you have a upwards force to balance it, so that means that you have a net lift. What are your thoughts on that? And you mentioned that to begin with, you thought that was a great idea, but maybe there are some aspects which weren't as good as you thought.
Yeah, exactly. What you said in the beginning, we thought what you said, like yeah, both wings producing lift, that's better. But in reality, you have to give space because what I mean is the canal has to solve before the main wing for the airplane to be stable, so that it pitches down when it's stalling instead of like
Yep.
pulling itself. Um, so you cannot develop all the lift capabilities of the main wing. So let's say I have it in front, but I'm gonna
Yep.
show it right like now. Like in this case, I don't know if you can see my
Yep, I can see. Yep.
okay. So as you can see, the canard is the one in like the shorter one, the smaller one.
Yep.
It's getting to a higher lift and higher CL, way higher than the main wing. So the main wing isn't developing actually all its capabilities of producing lift. So that really actually hurts the short takeoff. Capabilities again. That word. Yeah.
So just back on those graphs, what we were seeing was the pressure distribution over the span of the wings and the canards.
Oh yeah, sorry. So when we were designing the plane, we start with the airfoils before we could explain that afterwards. But we essentially try to design an efficient wing, and one of the main theory is that the elliptical distribution, like Prandtl and all that. Yeah.
Well, hey, maybe explain that a little bit for those who don't know.
Oh, okay. Well,
oh, that's I'll explain. Okay, I'll explain it. So the idea of a elliptical distribution is that as you go towards the wing tips, you should be dropping in the amount of lift that you produce, the circulation, in an elliptical fashion. The reason is because the induced drag is proportional to the change in circulation as you go along the wingspan, and the more elliptical that is, the more the induced drag will drop. That's the theory, and that was the idea that Prandtl came up with in, I think, like 1920, something like that. That has since been superseded by other really fancy wings, and including non-planar wings. So we're talking about a planar wing here, where you have just a one flat wing as opposed to having wing tips and things like that. So that's what we're talking about with elliptical distribution.
Yeah, exactly. Like, and for a given given wingspan, because if you like you said, like afterwards he discovered that if you weren't constrained by the wingspan but by the structure, then you could have like an shape distribution, all that. So yeah, since we had a fixed wingspan restriction, so we tried to design for that. So we actually achieve a very good result just designing the wing, as you can see for both planes, the one on the left, the canard one, and the one on the right. But then, of course, the other surface, either it be the tail or the canard, it affects the flow around the airplane.
Around the wing,
Yeah, over the wing. So it affects the distribution. So after including the canard, you can see that the beautiful elliptical distribution that we had achieved
is now butchered.
Yeah, absolutely butchered. So there comes like the conundrum that we were in that moment, because you see, we could fix both distributions, but like we have those propellers here, so we don't really know what the airflow is doing over that region of the wingspan. So
So at the front of the canard, you have like the airspeed that you're really flying on, right? However, when you go through that propellers, you gain some prop wash at the backward wing that can increase your efficiency in that wing, at least in that section. So we didn't have the time to prove that. Or to measure that even better, but it was the assumption we did, and it worked. I'll say so.
And the other thing too is that it also makes that part of the wing a little bit more stall resistant to the flow that goes over it.
Exactly.
So you get a slightly higher angle of attack and still maintain lift there.
Yeah.
Okay, that sounds very interesting. And then we'll come back to that one in a second, but now with these pictures on the right. So how does the one on the right differ to the one on the left? The goals of it plus the construction, because there's a V-tail here that I can see.
Yeah. So the DVF competition, the Design Build and Fly competition, every year changes its missions, right? So Dumbo was designed for a short takeoff mission that needed to carry the greatest amount of
passengers.
The passengers. Okay. You can see it right there. But holder. It's great because the competition really tried to simulate real cases of the actual world. So it was pretty great experience, right? Because you don't only have flight missions, you can also have ground missions. For example, in Dumbo, you needed to put the passengers in, put the passengers out in the fastest amount of time, right?
Okay.
So that will give you more points.
Yep.
So that's what another reason that we chose a Cunard, because we will have like the whole fuselage space to work
Yep.
on that.
Yeah.
Yeah, and
To place the propellers like right on the CG, which is, well, the thrust line right on the CG, which is very important if you're tilting it.
yeah.
Yep.
Mm-hmm. And for Hauler, you got obviously also a limited amount of wingspan that you could use. That it was 1.8 meters,
Okay.
and also one of the restrictions, no, one of the missions was to carry the greatest amount of payload that you could use. So that's why you see two bottles
Yep.
at the
Yep.
bottom of the wing that will carry actual steel.
Yeah, steel shot.
Steel
Okay.
shots.
Okay.
And in the inside, you have another bottle, internal bottle, with more steel.
Yeah.
So this aircraft was actually designed for that, to carry a lot of weight. And yeah, we wanted to go like full weight on that mission.
Yeah. Well, when I was talking earlier with Santiago, the numbers that you're putting out in terms of the weight were very surprising and impressive. So, could you go through the dry weight, maximum takeoff weights of these two? Because for those listening, it's it's quite impressive to hear the numbers when you think about how big or small these planes actually are.
Yeah, roughly, we can say that a Howler at its maximum takeoff weight was 15 kilograms, right?
Okay.
And the payload will be 50% of that. So it was pretty good.
Wow. Yeah. Really good.
Yeah.
And Dumbo, how
Mm,
did that compare in weight?
I don't remember Jumbo that much.
4.5, 5 kilos empty,
Yep.
Mm-hmm.
7.5 with the payload, if I recall correctly. Somewhere around that.
Well, a 30 centimeter takeoff with a 7.5 kilo plane is still very impressive.
Yeah, yeah, thank you. Yeah, it is.
Yeah. So coming back to Howler with the V-tail, why did you go for that design instead of a regular setup, and what were some major changes in performance because of it?
Okay, the main goal with Hauler was that, well, our main worry was actually drag instead of weight. Well, at least from
Yeah.
my perspective, was drag. So
Yep.
we were designing around reducing drag as much as possible. Our
Yep.
initial design was a little bit different. It tried to to have together like the elements of the motor mount, the landing gear, and the bottles, like all grouped up together like on booms.
Yep.
But then afterwards, the AAA said that that wasn't allowed, that you couldn't have any kind of fairing for the bottles for the
Okay. Yeah. Yeah.
so we had to change the design, and we focused on reducing drag as much as possible on other aspects. For example, one of the aspects of it is the detail, because it's kind of like you have, first of all, this wet surface for the same like projection for horizontal and vertical control. So that again, you also have less interference drag between the surfaces.
Yep.
So that's another advantage of it. Another advantage of it is that we expected this airplane to have like really tight turns to reduce the time of elapse, because that's one of the main criteria for the scoring, doing a really
Yep.
fast lap. So having a VTOL also allowed for, like, the wake from main wing to not
Yep.
blanket all the horizontal stabilizer at any given time.
Yep.
So that allows you to always have a great amount of the surfaces like into, well, is of course affected by the downwash, but it's like
Into the first term. Yeah.
it's like, yeah, into fresher air. And another point was, and I think we haven't mentioned this before in any presentation, is the spacing between the propeller and the wing.
Mm-hmm.
We also consider like how long it took for the prop wash to contract and to develop like to turn all its pressure energy into velocity, well, all, what it can be
Mm-hmm.
converted. So there wasn't a big like a high pressure bubble in front of the wing around the propellers. So we
Yeah.
also did that, and we tried to do fairings for the junction between the wing and the fuselage, but we
Yep.
didn't have enough time to do that, and also fairings for the wheels, but we didn't have enough time to do that. So
Yep.
yeah, basically that was like the main intent to reduce drag. Also the you can see that it's swept forward, and
Yep.
it plays a part on that too because as you know the as the angle of attack increases and the downwash
Yep.
increases, it starts like pulling the wake inwards. So like
Yep.
a span-wise flow, but inwards instead of
Yep.
outwards.
Yep.
So that will help us also like reduce a little bit the wake of the airplane.
Yep.
Yeah. I don't know if Mateo would like to add something else.
Yeah, no, no. As you said, the main problem right there was the drag, right? We're carrying so much weight that will produce so much lift-induced drag, so we needed to decrease it in other
Okay.
forms. So it was like that, yeah, yeah, yeah.
Yep. Okay. And the one on the left, Dumbo, you didn't have as much of a problem with the drag then to begin with.
Well, we for Dumbo we went for the short takeoff capabilities. We didn't think that much about drag, but it was a very draggy airplane, of course, because there are many. Well, first of all, you got the two wings. You got
Yep.
the four wheels landing gear, which is another point that we could talk about later.
Yep.
And as I was mentioning you before, the initial design had a problem that the canal was stalling like very prematurely, so we had to add
Yep.
some vortex generators to prevent that from happening. But as we were just like we were learning about it,
Yep.
we did them like a little bit bigger than they should, so that I think that really increased the drag on that airplane.
Yeah. So the thing in the competition is that if you didn't complain that a restricted amount of takeoff length, so your mission it won't be valid, right? So what we did is basically focus on that constraint, and we will
Mm.
manage the rest. That's the thing, yeah. And another thing that I wanted to mention is that because of time, this competition it's about 8 months from the release of the rules till
Okay.
the mission day, for to say like that.
Yep.
And so these aircrafts, I will say that they are not finished as we wanted to.
Yeah.
Uh, yeah, we wanted
That's
to do
always the
a little
case.
more.
Yeah.
Yeah, yeah, yeah. For example, in Dumbo, we still wanted to do um, like flight test, changing the CG position so we could do much better. Maybe we could play more with the tilt angle of the motors. For example, for Howler,
Yep.
we wanted to test those um, fairings for the landing gear,
Yep.
and the fillets between the fuselage and the wing. So a lot of things that we didn't have time to do it, but it will be much better, of course.
Yep. So just back on the canals thing, I would like to go through that a little bit more and flesh out what it means. So you're saying that the canals were stalling before the wing. So why is that a bad thing? Why would you want the canals to stall after the wing, or even the inboard part of the wing compared to the outboard part of the wing?
Well, you absolutely wanted to stall before the main wing, but the problem was that it was doing it very, very early on. So let's say during the approach, the airplane started like doing a bobbing motion, like dropping the nose, picking
Okay.
speed,
Yep.
and yeah, like a fugal motion, a fugal motion.
Yep.
So we needed to decrease that, and we didn't have time to redesign everything. So like the quickest way to get out of that problem was using the VGs.
The vortex generators, yeah. So could you explain what vortex generators do and what your design was? Were they simple triangles, or did you use co-rotating, counter-rotating? What are the differences between those?
Okay, they were counter-rotating. They were big VGs. They weren't like micro or anything. And
Yep.
what VGs do is that they they kind of grab air from the free stream that is not like
Yep.
slow down into the boundary layer, and they mix them up with the boundary layer. So they re-energize the boundary layer and allow for
Yep.
the flow to stay attached to the wing for much longer. That's basically like the
Right.
main principle of the VGs.
And you mentioned micro vortex generators compared to regular vortex generators. What would be the difference in performance and the benefits of each?
Well, the big vortex generators, for sure, they completely make sure that the fresher air is mixed into the boundary layer. And the micro ones, they might be enough to trip the flow, and they may cause, or well, they definitely cause much less drag than the bigger ones.
Yep.
So I
Yeah.
think yeah, sorry.
Yeah, sorry. For example, some people even use like sandpaper
Yep.
in some positions of the wing to even I mean like re-energize the flow in that section. We didn't use that. We used the big VGs as Santiago said. Yeah.
Yep. So just a bit more on the topic of sandpaper and that. So the nuance is that sandpaper is tripping the boundary layer as opposed to the vortex generators. It doesn't matter whether the boundary layer is laminar or turbulent yet, it's going to pull in high energy flow and put it into the near wall flow. So it's a slight difference, but they both can achieve the exact same result if done properly or done
Yes.
in a certain way.
Yes.
Yeah, and
Fair.
that was the other thing. Like I said earlier, like we didn't have enough time to iterate because we only could go and try flying like every, I don't know, Mateo, like when Felipe, which was the pilot who helped us here, could fly. So we didn't have many opportunities to try different things. So we went
Yep.
for what was like more secure.
Yeah, that's true. So with these two wings, I was curious about the profiles, the airfoil profiles you were using, and what they were, what the differences between the canard compared to the wing, compared to the Dumbo Howler, and what the reasons why you went for these different profiles.
Okay, so like for choosing the profiles, the first thing that we do is we go to a repository. The one I like to use is airfoil
Yep.
tools, because it has the plots, the polars and everything.
Yep.
So we start like with a very conventional airfoil that's commonly used for model aircrafts or like UAVs, like NACA
Yep.
2414 or something like that. And we start comparing airfoils into that range of thickness, because also you gotta take into account the thickness for the structural part of the plane. You wanna like
Yep.
a big, yeah, a thicker spar. You don't want like a very flimsy wing for these kind of things.
Yep.
And also you look for the airfoil appropriate for the Reynolds that you're going to encounter in the UAV. So we start filtering on that. We pick the better ones, and then we bring them to X-foil or XFLR5, which is basically the same. That uses potential methods, but it also couples like some viscous effects and viscous boundary layer like modifications to it.
Yep.
Mm, and we start like evaluating for the purpose of the airplane or the purpose of that segment of the wing, which is like the more appropriate, like you said. And for example, let's take a howler because as an example, because we reviewed many more airfoils for that one. Mm, we went for the MH70, which is the orange one. I don't know if you can see it properly, but there are two lines for each of the airfoils. The solid line is for a Reynolds of 1.5, like 1,500,000.
Yep. 1.5 million. Yep.
Yeah, 1.5 million. And the dotted line is for 500,000.
Okay.
No, sorry, for 100,000. 100,000.
Okay. Yeah. Yeah.
Yeah, like to cover the range, because we actually tried for every single, well, like with a like a finer spacing, like 100, 2,000, 300, 400. But for the display, we only have like the upper and lower ranges. Um, so you can see that there are airfoils that in theory, like the CL over CD, is much better. For example, the pink one, which is the SD7062. But if you go down and have a look to the CM polar, you see
Yep.
that the CM of that airfoil is pretty big, which means that the airfoil really wants to like nosedive.
Yep.
So if the airfoil has that amount of like uh, let's call it like a moment, then
Yep.
you will need like a bigger tail or a tail
Yep.
that's like producing more downwards force to counteract that. And then you start having drag from the tail. So as we said earlier, we wanted like to minimize drag, so we had to find the balance between like structural, aerodynamic efficiency, but also this kind of thing that like involve other concepts that aren't just like the CL over CD.
Yep.
And so for this one, we picked one because like was like right in the middle. It wasn't too bad CLCD for CLCD. It wasn't too bad for the CM. It wasn't too bad for the drag. Too bad for the CL. Like it was like in the middle ground. And for
Yep.
Dumbo, because it had a canard, and we were like trying to load the canard, we went for a very lifty 7062 SD 76. Sorry, SD 7062.
Yep.
Um, but yeah, maybe a wing with this moment would have helped us also in that regard because, as I told you, the canal was being loaded way more than it should have.
Yeah, yeah. So back on the. Oh, sorry. Would you like to say something, Mateo?
Yeah, would like to say that maybe if you're starting designing your aircrafts, maybe you will ask the question like, which Reynolds should I choose, right?
Yep.
Because you have the range, as Santiago said, from 10,000 to, I don't know, 2 million, 3 million, right?
Yep.
The thing is, we divide the aircraft design stages in three that are conceptual, preliminary, and detail, right? The conceptual stage is basically when you don't use any particular airfoil that you don't want in the early stages of your aircraft design to fix, right, or to constrain
Yep.
your design. So basically, what we have in the images here is basically what we call a sensitivity analysis.
Yep.
So we have to take into account that we are designing an aircraft for a mission, for some missions, right? We're not designing an aircraft because we wanted to have fun. So that's the thing. You have to put that score, how you will score the most points of the mission into math equations and map it like you have in the screen. So you will basically see which space that's called the design space that you have
Yep.
there we want to choose, right? And you can also compare it. For example, that's what we did with aircrafts that had already participated in previous competitions. So basically, the starting point will be this constraint analysis that you see here. It's basically a plot of thrust to weight and wing loading in the x-axis. So here
So the
you
bottom
will
left figure, or bottom left and bottom right.
exactly, yeah, they both are at the bottom. So basically here you will say, oh, okay, we need something like that, and you can start like trying different speeds that you could be competitive, right? And then you will see, okay, so we will maybe fly at 30 meters per second, and you can already start translating that into Reynolds. That's the thing.
Yep. So, back on the Reynolds number, you were saying, Santiago, that you did some X-foil analyses for a bunch of different Reynolds numbers from 100,000 upwards. And the two that were on the graph were the 100,000 versus 1.5 million. So what were the differences in terms of the flow over the wing, and why is that important to go for such a big range as opposed to going for 100,000 as you first mentioned?
Okay, so when the Reynolds is higher, the flow has more energy to stay attached to the wing, so you can like squeeze more lift out of it, and it also, as it stays attached, like much better, the wake is also smaller, so you got less drag. What's the other question? The other question, sorry?
And then you mentioned that potentially like 500,000 a Reynolds number instead of 100,000. So these two Reynolds numbers that you have on this plot are spanning quite a big distance, and they actually fall into two different types of flow regimes. And why is that? Why did you plot these two?
Okay, because we then modeled the aircraft in XFLR5 to analyze different behaviors of it, not just
Yep.
also dynamic. And
So by dynamic, what do you mean by that?
oh, could we touch that point later?
Sure. Okay. Yeah. Sure. No worries.
Yeah. So we gotta evaluate all the flight envelope of the airplane. So you get like the large chord of the root of the wing flying at the maximum speed, which gives you a really high Reynolds number. But you also have the wing tips or the tips of the control of the stabilizer surfaces at landing speeds or at stall speeds, which are very which gives you a very low Reynolds number. So you gotta make sure that the airplane behaves like how do you say that, like good,
Stably. Yep.
stable, and it has a good behavior in both the higher regime conditions and the lower regime conditions, and also because the software interpolates with the results that it has from the 2D airfoils analysis for the 3D model of it's the potential method, but in 3D it interpolates the Reynolds that it has stored. So maybe fewer is enough to interpolate, but the finer the resolution, the better. One thing that I didn't mention is that when we're analyzing the airfoils, is very important to do a mesh convergence analysis, because otherwise the results that you're getting may be or may not be the ones that are like close to reality. They're still like just potential methods, and at the end of the curve, at the end of the CL curve, it's not that reliable. But at least on the linear part, you get a much better result if you start increasing the mesh density and checking when things converge, basically.
Yep.
Yeah. I would also like to say, as Santiago said, you have to account for the whole flight envelope, right? Your aircraft doesn't spawn at first, and your aircraft can be great at cruise conditions, but if you never take off, so you don't really have an aircraft, right? So yeah, you have to manage that things.
Yeah. So the Reynolds number range was there to cover the entire range, so that hopefully it will perform well enough to take off and cruise.
Yeah.
So back on the dynamic, would you like to talk about the dynamic motions now or at a later time?
Well, that's fine, okay, but that's fine now. Yeah, we got the slide here. So, would you like to talk a little bit about the dynamics, Mateo?
Okay, no, so basically what we did is basically search for how we can quantify our stability, right? So this is very common, our basic plots that called a root locus, right? So you can say if your aircraft is stable or not, and how much is stable or not. So yeah, basically what we did is search for previous aircrafts that could have like some values, for example, damping ratios, frequencies, that we can fix our aircraft into those values, so the pilot doesn't complain, right? So it's pretty difficult that you design an aircraft great, but the pilot will say, I don't feel it great. Yeah, right. Your aircraft is unstable. I need to do a lot of work trying to stabilize it. So that's basically this plot. And this is not only aerodynamics properties. This also includes inertia properties. So how you distribute your mass around your aircraft, right? So if you have, for example, more mass far away from your center line, for example, you will have an easier stability because it's more difficult to change, right? your attitude. So yeah.
So yeah, so basically when we start designing the airplane, we start by the doing the wing, and then we follow with like yeah doing the tail. The important thing is like going step by step. The first thing that you gotta achieve is static stability, because if you don't have static stability, you won't be able to have any dynamic stability.
Yeah.
You gotta have a CM curve that has a negative slope, which means that, for example, if the airplane pitches up, then there is a restoring moment that wants to pitch the airplane back down.
Yep.
So once you achieve that, and once you achieve a trim point, like around the alpha that you want to have for your airplane, for example, we always, well, not always, but we generally aim for zero, so like a zero alpha for the whole airplane, because it's easier for us later on to design on CAD things and for the like the thrust lines and everything. So it's easier to set everything on zero. But yeah, once you have the stable, like statically stable aircraft, you go on
Yep.
to checking what Mateo was explaining, the dynamic stability, which are basically two, which are like longitudinal stability and lateral stability.
Yep.
And there are different modes for each. For longitudinal, which means like on the pitching axis, there are, well, two, which is like the short one, which is like rapid oscillating motion, like in pitching around the pitching axis, and the slow one, which is phugoid, which
Yep.
is like longer oscillations. For example, let's say that the airplane starts pitching up, and then what follows is that we'll start losing speed. As it loses speed, since it is statically stable, it will start to pitch down and gaining speed back again. And once it gains speed back again, it will start pitching up, and it forms like these oscillations, but like slower than the other one. That's like the longitudinal one. And the lateral modes, there are three, which are the short mode. The short mode is like the rolling, but
Yep.
yeah, for very 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 high frequencies. And then you have the Dutch roll, which is very
Yep.
interesting, because it's like, let's say that the airplane goes to the right.
Yep.
Then the left wing will gain more lift, so it will start rolling to the right too. And then because the airplane is stable, then it will start like drifting, like falling to the right.
Yep. Yep.
So now the right wing is going to start getting like a larger alpha and more lift, so it will start rolling to the left, and since it
Yep.
has also more lift, it creates more induced drag, so that wing is also moving backwards, so it's going in the opposite direction, and it's all like doing like I don't know how to call that motion.
It's kind of like a fish swimming and rolling at the same time.
Yeah, exactly.
Yeah.
You have that one, and the spiral, which is that basically the airplane is start like slowly banking and
Yep.
spiraling down to earth, which is called the spiral. So one thing that I wanted to talk about this part of stability is that oftentimes like the term what's it called, like static margin,
Yeah.
I
The
think it
static
is.
stability. Yep.
You could have two airplanes with identical static margin, but once you get to the dynamic behavior of it, they could be completely different, and that may be due to a number of things. Like the ones that I have in mind right now uh, are the like the aspect ratio of the tail, for example. You can have two airplanes with the same wing, same static
Yep.
margin, but as you may know, the higher the aspect ratio, the higher the slope of the CL of the wing. So if you have a higher aspect ratio tail, then it will react like more abruptly, we'll say, or more like strongly to. Or another very important part is like where you place it in relation to the wing, because the downwash it's like a field. It doesn't have the same strength along like around. Yeah. So if it's like where the strength of the downwash is the strongest, it will have like the highest amount of downforce on that part of the tail. But if you take it out of the wake and put it like up or down or further away in other ways, you can still have the same static margin, but an airplane that would behave completely differently.
So for these graphs, you're also talking about it wasn't just the aerodynamics, but also the construction approach. So the distribution of material and also the stiffness of things. So you 3D printed these planes, that's right?
Well, not completely. There are some 3D printed parts of it.
Yep.
I think we could jump to the Would you like to talk about manufacturing now, or we could like...
Yeah, if there are other aerodynamic aspects you'd like to talk about, feel free to talk about them. Otherwise, we can jump to the manufacturing if you prefer.
Oh yeah, let's continue with the aerodynamics and then jump to the
Yep. Sure.
Okay, so for this part, we need to... What we like to do is a performance analysis of the aircraft, right?
Yep.
So our first year in Dumbo, we did like a limited amount of analysis, because we didn't know that much, right, at the time. So we basically only did like a takeoff analysis with different takeoff weights. We can see there how much weight does Dumbo carry. Yeah, we have like 2 pounds, 12 pounds. Yeah.
Okay. Yep.
Yeah, so that's our maximum takeoff weight for Dumbo, and also because the circuit that we use in the competition, you need to do like 180, then a 360, then another 180. You have to account for that turn radius, right? You don't want your aircraft to go 1 kilometer only to turn. So that's the analysis that we did in the bottom image at the left. But for the next year, for Holder, we did much more analysis. So as we were concerned about the drag, we did first a drag decomposition. We use different softwares. We use, as Santiago said, Xfoil, XFLR, R5, and sometimes we use also OpenBSP. OpenBSP is a great software. You can do a lot of analysis, structural analysis, error analysis, a lot of stuff. And you can also create a drag buildup that you see right there. So I wanted to mention, for example, for our landing gear, we used a carbon fiber tube for our nose landing gear. So you can see right there how much drag that will cause in the aircraft. For example,
By
for mission
NGL, nose landing gear.
Yes,
Yes.
in NLG and in MLG. So that's about how much that is. It's like 35% roughly. So that's a lot.
Yep.
That's why we wanted to do some fairings for the landing gear, because it's a blunt object that you have in the aircraft. So yeah, we wanted to minimize that, and also in the image that's down, we also try to manage to put our aircraft to fly at a certain speed that will cause the less drag, right?
Yep.
So that's what we see in figure 29. We said basically our aircraft is trimmed at that point, will fly great at that point, and will cause the less drag, right?
Yep.
And no, it's okay. Go.
Okay, so at that point it's usually called for general aircraft, for the general aircraft world, is the glide speed, because it's the one like that offers you like the least drag, and we chose that for this competition because you're not only constrained for the dimensions of the airplane but also for the propulsion aspect of it. including the battery. So we had a limited amount of wattage, like how to say that, like watt hours,
Yep. Yep.
watt hours
Yep.
of power. So well, later on you'll see we fell short, like for a couple of seconds, maybe 5 seconds.
Yeah.
Yeah, we had to optimize to do the laps as fast as possible, carrying the most payload as possible, but also being able to complete all the laps.
Yeah.
Yeah. And
So
the
on
Yep.
these graphs, so let's explain what they are a little bit more. So there are three lines. There's a yellow line, a dark red, and then a regular red.
Yeah.
The dark red is the parasite drag, which is the combination of skin friction and profile drag. The yellow is the induced drag, and then the regular red is the total drag. So could you explain the difference between these and why they change with airspeed so much?
Yeah, for example, the left one is basically when you do an analysis with fixed weight. So that's
Yep.
basically computing how much drag you will produce
Yep.
to lift up that speed, that weight, sorry, right?
Yep.
And the red one, the dark one, yeah, it's basically like you have that's you start, for example, with your minimum CD, right? Your minimum drag coefficient, and
Yep.
as you know the formula for the drag, it will increase as you increase your speed quadratically. So that's basically what we have here, and basically the total is basically the sum of that.
Yep. So
In other words, like the induced
Yep.
drag is the one like derived from lift, and as the
Yep.
airplane starts flying faster and faster, it will need like a lower and lower angle of attack.
Mm-hmm.
Yep.
That's why the induced drag start. Well, I don't know if that's why, but that's one of the.
Yeah, it's increasing. Yeah, because if you're going slow, you will need a lot of lift coefficient that will cause a lot of drag coefficient, right? But if
Yep.
as you're going faster, you will need less lift
Yep.
coefficient. So that's
Yep.
why it decreases.
Yeah. And then for the parasite drag, as you go faster, the skin friction increases.
Yeah, skin friction, exactly. Yeah, all of that. And in the in the last table, you will see like you have a LD of 6. That's terrible, and yes, it is.
Yeah.
It is terrible. The thing is, the aircraft is not only the wing and the tail, right? We have two bottles really exposed outside of the aircraft, and you can also see a red wing.
Yeah, I was going to ask about that.
So the mission for the last year of the competition, you will have to drop another aircraft from the main one. So, yep. So the one that you have at the bottom of the fuselage is basically an autonomous flying wing that we designed.
Okay.
So when you hit a certain point of your circuit, you will release it, and the aircraft by itself, the aircraft is not really controlled. It
Yeah.
will need to return to the launching point by itself, right?
Okay.
So that
I don't know if you can see it,
Yeah, I can see. Yeah.
it's like a little point, yeah.
Yeah.
like right there.
So when this was attached to the rest of the plane, was it also providing a certain amount of lift to compensate for its own weight, or was it just okay?
I mean, what we wanted to do is that the aircraft, the pilot doesn't feel a difference, when you fly it without or with the flying wing, right?
Yeah.
So basically, what we did in the mounting of the flying wing is basically do not create any moments, do not create any forces. You will only be there producing drag.
Yeah.
That's basically what we try to aim for.
Okay.
Take of the glider because
Yeah.
the structure of the glider isn't that strong, so it wouldn't withstand like an angle of attack that would produce like force on the wings
Mhm.
at the speed
Yeah.
that the larger aircraft was supposed to fly, and also as Mateo was saying that the pilot perception or how the handling the flight qualities and the handling qualities of the airplane were very important for us because our pilot didn't have the opportunity to fly the airplane beforehand. So
Yeah.
and then go to the States, and there we would meet would meet the pilot, and he will have like basically a flight for the first time in the competition, basically. So
Yeah. And
Yeah.
that's a lot harder than it sounds.
yeah,
Yeah, the thing is that we could say like, okay, we can try to fly it by ourselves. The thing is that in a competition you have limited resources and time, right? It's difficult to spend time and resources on trying to teach someone how to fly these heavy aircrafts because it is not the same to fly
No.
like a small flight test aircraft, right? And yeah, and like a foamy, it's different to fly a 15 kilograms aircraft,
Yeah.
right?
One big difference is that with the bigger ones, you usually have a lower thrust weight ratio, so you don't have a lot of margin of error. Whereas with the small ones,
Exactly. Yeah.
you can get a high thrust weight ratio. So if you get in trouble, just pitch up and you're good until you get
Yeah.
more speed.
totally.
Yeah. And the wing loading was too high because we need to carry a lot of weight. So you have to be very careful on what maneuvers you do. So that's
Yeah.
why we basically our pilot was from the University of Embry-Riddle. He is a friend of ours, of our
Yeah.
group. So what we did is basically fly with our test pilot here there in Colombia and tell what the pilot felt at the flight test and tell him
Yeah.
what he needs to know beforehand.
Yeah, we had two pilots, one here and another one there. So yeah.
Okay.
Okay, this is for the power, right? This is the power graphs that we used. In the left side, you will have for Dumbo.
Okay.
Okay, so basically our workflow is basically go from the conceptual stage to train a preliminary stage, right? And you will have now numbers of the drag that will produce, right?
Yep.
By that, you can start sizing your power subsystem, right?
Yep.
So what we do is basically start from the propeller because the propeller is the one that will reproduce the necessary thrust that you need at the
Yep.
speed that you need, right? A lot of people, for example, have that misconception that yes, you can have the highest static thrust, but if you need to fly faster, maybe that propeller isn't appropriate
Yeah.
for direct.
The advance ratio will affect its thrust.
Exactly. And that's basically what we have there in the graph. You can see how we try to manage our peak efficiency point to match our cruise point. So basically we will have the best aerodynamic efficiency and our best power efficiency at that point. And for the right side, we have the same. As you can see there, our propeller is pretty high in pitch. It's a 16/14. It's pretty high.
Yep.
So it was actually that was one of the propellers because I think we finally used a 16/16 propeller. It was pretty high in the pitch.
Yep.
Because we needed to go so much fast. That's the
Yep.
thing.
Okay. So why did you select A16 instead of anything other for the diameter?
That's the bigger one we could get.
That sometimes that is the case. Sometimes that's the biggest one you can get.
You know, in the competition, as I said, you need to manage your resources, right? And
Yep.
we managed to have a partnership, we can say it like that, from I don't remember, from T-Motor, right? So we can use like a discount code for our university project. And
Yep.
basically, we constrained our design to certain range of motors. When we start searching for that motors, for example, the diameter of the motor, the kV of the motor, all that, we basically said, okay, we have that power available. We can start searching the propeller that we can use to extract our and the price too, of course. Yeah.
Yeah.
In Colombia, it's very difficult. You don't have a lot of resources.
Okay.
You need to try to do your best aircraft with the lowest amount of money.
Yeah.
So that's the thing. Hmm.
So your motors that you used, what kind of KVs were they, and what batteries were you using with them?
This is another interesting thing because the battery, as we needed to travel from Colombia to United States, you cannot go above 100 watt hour, right?
Yeah.
So basically, we had a battery that was 19.9 watt hour. 19, no, sorry, 99. 99.9, yep. So we were at the limit. It was a 6S battery.
Airtrain Republic brand?
No,
Like
the capacity.
With 6S, it would be
Uh,
something like 10 or 15,000 milliamp hours or something to get a 99.9 watt hour battery. It'd be huge.
Yeah, it was something like that. And I don't remember. It was like 4,000 for. Okay, so yeah. Basically, take 100 watt hour and divide it by, by the voltage, and you have that. So yeah, that's why we use that. And basically, the diameter of the propeller was you are producing the amount that you need for your thrust and
Yep.
the speeds that you need. Okay, so that was enough for our decision. Mhm.
Okay. And what softwares did you use to calculate these graphs?
Actually, we were using APC. APC is a pretty famous
Yep.
brand for propellers, and they have a
Oh, okay.
great performance data
Yep.
like database. So
Okay.
we downloaded all of that and start searching propeller by propeller. At which RPM are we operating? Which velocities, and that's how we reconstruct the graph above.
Yep.
Hmm.
Yeah, I understand. Yeah.
And that's actually one point that I think that we should improve in the future, because one thing is the data from the propeller, and another thing is the data from the motor manufacturer.
Yeah.
Yeah, but everything together is a completely different thing. It's just not like sum it up and that's it. No, it's another thing.
Yeah.
Ideally, we should test for the complete propulsion system, including the ESC and the battery and everything, because yeah, it may vary a lot.
Yeah.
Yeah, some of the things that we also try to do during the competition is try to do a thrust bench, right? And we actually did it, an static thrust bench test. However, the thrust benches got destroyed. I don't know what happened. I don't know if it was that.
Don't let the electronic guys build the structure for the test bench.
No, it's okay. It's okay. No, because it's an error of all. If we saw something that it can failure, we have to account for that, right? We need to make the call. So careful, guys. Maybe something happens. So
Yeah.
basically, what happened is that I will say the torque of the motor, the propulsion system, basically broke the thrust bench. So we had an incident there. Nothing happened.
Did it?
And everything caught on fire, but nothing.
Yeah.
Oh,
Yeah.
wow.
We saw a great spark because
Yeah.
we were like drowning like 100 amps. So it's what it was a great spark, a great white spark. I think I will never forget that. But
And
the thing is that
Did the
Yeah.
load cells break? Like, it was a physical break that then cut
Yeah.
everything. Like the okay.
yeah. I mean it deforms a bit, and that cut
Okay.
the cables from the ESCs and the battery. So it was pretty chaotic.
Yeah.
Yeah, that's something that we now know. And basically, what we wanted to do with that truss bench, it was putting it at the top of a car. Because, yes, you have static data, but as we said before, it is
Yeah.
not the same, right?
Yeah.
Uh-huh.
That's clever.
So, and we don't have really a wind tunnel at our university, so we can't access something like that. So our solution was, let's put it at the top of the car with some airspeed sensor, and let's test. And that was basically our idea.
Yeah. So the idea for those watching who haven't thought about this is, if you put it on top of a car and you can drive along, you can simulate an airspeed, so then you can figure out how much thrust you're producing at different advanced ratios, at different airspeeds for your propeller. So it's not just static, is what Mateo's talking about here, which is a very clever idea.
Yeah, yeah. We didn't have time really to test it, but it's difficult to do a lot of things. Some of the tools, you don't have a lot of the tools, right? Because we were the first ones in our university to do that stuff. So
Yep.
you don't have all the facilities to do that stuff. So
Yep.
it's okay. Hmm.
So this was your GPS circuit, it seems, on the bottom left.
Yeah, that was the maiden flight of Dumbo. It didn't follow the trajectory from this competition. We only did like as the pilot wanted. If the pilot wanted to test that stuff, we said okay, it's okay. And this is basically some tables for the performance that we could extract from our data. The next year for the holder, we have a lot of more data. So we have GPS, we have airspeed sensors, we have the power that we're draining from the
Yep.
battery, a lot of much more stuff. So yeah, that's basically what we have there.
Well, there's a lot of information here. What stands out to you as impressive? What parts are you proud of here? Because there's some pretty interesting things like rate of climb, 50 feet per minute. It's pretty decent for a small plane.
Yeah, I will say I'm super proud of Holder. I'm super happy of Holder. And that being said, it wasn't our final aircraft, right? So the thing is that that aircraft was so fast. It was the fastest aircraft that we have ever do. The heaviest too. I don't know. It was a lot of stuff. For example, the glider that we did also, it was autonomous. That the first time we encountered something like that at our university too. So it was I would say a lot of steps open for our research group. Yeah.
So the max airspeed was about 40 meters per second, so approximately 150 kilometers per hour, something like that.
Yeah, at level flight. That's the thing. We could dive. Yeah.
That was here, and the pilot here didn't push the airplane like for
Hmm.
with a full throttle for more than 2 seconds.
Mhm.
So we're not sure.
Yeah. Yeah.
So Santiago, what part are you most proud of? Mateo told us his howler with the max speed. What are you most impressed with it?
About Howler or about?
Either one, because you're part of both of these teams.
Well, we haven't piloted them. We built them, but we didn't pilot them, sadly. Uh, I think I was very impressed with Dumbo because it was extremely weird, extremely hard to do, and to make work. Having an old flying canard, having tilting motors, and having like everything, the weirdest thing you can imagine, like 4 wheels instead of three, like for the landing gear.
Yep.
Like the weirdest airplane that we built.
So why did you use 4 wheels for the landing gear?
Oh, that's interesting question. Because as we told you, we didn't have the luxury to train with the pilot. Well, the pilot was actually trying to fly, and we also here had like a grass strip, which is very bumpy.
Yep.
We were thinking that well, we only have one chance. We can't screw it up. So if the airplane maybe lands like a little bit like off, we can risk damaging the canard. So that's why we went for a 4 cycle instead of tricycle. Basically to protect the airplane.
Okay.
Yeah, something that I want. Okay, go Santiago. I want to mention something also from our pilot at the United States. The first time that he flew our aircraft, he said, "Wow," because he didn't need it to do anything in the aircraft. He didn't change the CG. He didn't trim the aircraft. Everything was great. So that's difficult for a pilot I mean, it is not a commercial. A holder wasn't a product, right?
Yep.
So it's great and pretty satisfactory to hear from your pilot that your recovery is great. Yeah.
So would you say you learned a lot from Dumbo to then use for Howler to make it pretty much perfect from the start?
Yeah, Howler was easy.
Yeah. Yeah. Yeah.
One thing that I want to mention that we haven't touched is the thrust line, because I saw that you mentioned it in one of your videos, and we also had that into consideration. Is that we usually like
right.
to align the thrust line of the motors with the CG and the
Yep.
drag center of the airplane, so that when the pilot changes inputs, like for example a throttle input, it wouldn't
Yep.
pitch down or up, or if
Yep.
it's flying at a different regime, then the difference between drag and thrust and the lever between those, if they're like offset, wouldn't cause the airplane also to pitch down or up. Um, Mateo, would you like to talk about the counter-rotating propellers and how they help?
Mm, okay, so basically, in the propeller, you will. Yeah, it's difficult to explain without a graph or something like that. Yeah, but it's basically you don't want to affect that much the the wing loading, right?
Yep.
The wing lift distribution of your wing. So basically, what you need to do with your propellers is basically load more the center of the wing and not your tips. That's why you need to, for those propellers to spin in a certain direction. In this case, to the inside of your,
Yep.
to the fuselage, to say it like that, and not your tips, because that will, you know what happens when you load your tips, you can go into a tip stall and you
Yep.
can lose your aileron control. So that's
Yep.
basically,
And at the very least, you can increase induced drag anyway.
Yeah.
yeah, that too. Mhm.
But here as well, so what you're saying is by having counter-rotating propellers, you're symmetrically loading the wing on the left and the right, as opposed to if you had co-rotating, one's going to be loaded a little bit differently as well, which would then change the rolling moment of the plane as well.
Exactly, and also
Yep.
you're doing the same thing, like regarding P factor and gyroscopic precision and the prop wash, like hitting the tail.
Yeah. Yeah. It's all symmetric, yeah.
Exactly.
Yeah, well, actually, for Dumbo, the first test, we didn't have a counter-rotating. I mean, counterclockwise and clockwise propellers. Yeah, so the first test that we did, it was both of them counterclockwise or clockwise, but both were the same. And we actually saw in the flight test how the aircraft tend to lower a wing.
Okay.
Do you
Yep.
remember, Santiago?
Yeah,
That the aircraft like
to the same side always.
yeah.
Yeah.
It was all like oscillating in the roll axis. So it was pretty weird and sketchy. But we later changed the propellers and it was okay. Yeah.
Okay. S- Oh, this is your loading testing, your strength testing.
Yeah, for
Yeah.
the wings. Yeah, we did for both airplanes. Obviously, for Howler, it was a much higher load, and also for the tail. And the test for the tail, we didn't have it planned, but we had an accident. Shut this up. We had an accident with the first version of the airplane, which was the after the maiden flight, which I think I have shown. I don't know. Let me show you.
I think not yet. This is the one. As you can see, the runway is pretty.
Bumpy.
Yep.
Yeah.
Yep.
So after the maiden flight, I don't know why we wanted to have a bigger tail or a bigger surface control.
Yeah.
I don't recall exactly why we decided that, but we decided that we needed a bigger control surface for the tail. So what we did is that at the end of the stabilizer surface, we added, like, these control horns.
Yep.
Yeah, we added those to increase the surface area of the control surfaces.
Yep.
It went really, really wrong.
Yeah.
Yeah, it generated like an aeroelastic oscillation on the tail, so strong that it broke the tail in mid-flight. So the aircraft
Okay.
crashed, and after that, we decided, yeah, that we needed to do some testing.
Hang on.
We eliminated the control surface, of course, and we also tested for the strength of the tail.
Yeah. But back on the bumpy runway, so you've shown 2 takeoffs. Did you have any takeoffs where you had a problem with the runway, or was your plane completely fine with it from the beginning?
I will say for the landing, we have the problem.
Okay. Okay.
For holder, I think Santiago has the landing part. Yeah, where basically our nose landing gear went like it bent basically.
Yeah.
You can see, yeah,
Mm.
like that. So the aircraft stayed like that. So
But that's still quite
it's-
good. It
Yeah.
handled the rough runway very well.
Yeah, yeah. I think it is very difficult, for example, for the Dumbo competition, because there you have not a straight surface, right? But in the United States, yes, you have a great runway, so
Yeah.
where you can take off. So that's something else that we didn't take into account. I mean, we knew it will be better, but not that much, right? Because okay, you are accelerating to take off in Colombia, in
Yep.
our Colombia runway, but it is bumpy, so more friction, a lot of that, a lot of that. And United States, no, it was a pavement runway, so it was great. It
Yeah.
was pretty different. Yeah.
We could see that just there how the plane was bumping a lot, so the lift on the wings would have changed dramatically throughout the takeoff, and then finally you got like
Exactly.
enough.
And
Yeah.
actually, this maiden flight was a fast taxi test. It wasn't even the intended to fly.
Yeah,
Okay.
that always happens. I don't know why our aircrafts or our pilot maybe because he said like okay, let's do a taxi test to the end of the runway. I come back and try to take off, and then you take off. So it was yeah.
Maybe the wheels needed to be worn in or something with the axles. I don't know.
Yeah.
So that's the end of the aerodynamics section of your design.
Oh, let me check. So I like to show the videos. And let me check. Yep, it is.
Okay.
I will say the CFD part, Santi.
I forgot that.
Mm-hmm.
So here,
Okay, yep.
I missed it. Here.
So these are the bottles under the wings, mostly the CFD of them.
Yeah, we tried different bottles because they had to be commercial bottles, commercial water bottles.
Yep.
Yeah, soda bottles, and we were trying different configurations of each of them, and not only in isolation but in conjunction with the wing where they were going to be placed, because
Yep.
it's not the same like putting them like a little bit forward, a little bit after, or maybe also, as Mateo was mentioning earlier, in the part of dynamic stability, how far away you put them from the CG, it also hinders the stability in roll.
Yep.
So all of those things had to be taken into account. We didn't want them to be right on the prop wash either, but we could
Yep.
far away. So it's a very like difficult problem to solve. Thankfully, we this time had the help of 2 guys, which are Daniela and Mateo, another Mateo now, and Daniel Ramirez, who helped us with like the CFD. And yeah, they were in charge of this part.
Yeah, they used a open foam, I think it is, right? And
Yep,
ANSYS.
yep.
Okay. So yeah, it was great analysis because they did like a grid of different positions that we could have the bottle and
Yep.
test it. So finally they said, okay, this is the best one is that we could use. Okay, let's go for that.
Okay.
Mhm.
So in these locations, were any of them improving the lift characteristics of the wing, or were they all detrimental?
Well, we're gonna have to call them. but
Okay.
but as far as I know, for the L over D, they were always detrimental.
Yeah.
Okay.
Mhm. Yeah.
So yeah, if you'd like to, oh, okay, this is the system for the wing, for the bottles. For the ground mission, it had part of it was like putting in and putting out. I think putting out. I don't know if putting out, but putting in the bottles as fast as possible and like loading the aircraft with like everything, the outside bottles,
Yep.
the inside, the one in the inside, and the glider. So having like a fast, quick method of putting them in there was very important, and also the release mechanism of the
Okay.
was very important because
Yeah. And it needed to be really robust because you have like you have like 4 kilograms in each bottle, so it was pretty
Okay.
heavy. So you have to account for a hard landing, right?
Yep.
So, for example, if that bottle falls off when you land, the mission didn't count. So you have to take that into account.
Okay.
Hmm.
So this is they're 3D printed then those parts.
yeah, those parts are.
Okay.
I think we can go to the manufacturing part because there is a lot of 3D printing stuff.
But let's first like show a little bit of the flight of Dumbo.
Okay.
You can see
Yep.
there, yeah. You like to see it, and well, in this flight it was pretty stable. It was a little bit difficult to achieve because finding the correct CG was a little bit troublesome for us, because we were just like learning stuff and we were trying to use the typical rule of thumb ideas, but those don't work with canards. Um, so we have to play a little bit with it. We try to get to the proper location via various ways, like the just handwritten formulas, some XFLR5, some including the DATCOM. I think we checked some of the Canard airplanes that, like for example, the Air Force tried to do unsuccessfully, like the U.S. Air Force. So it wasn't an easy problem to solve, but yeah, here it's stable, and yet, if you can see here in the landing, it's not bobbing, it's not like pitching up and down, but it's
No.
like moving like in the roll around the roll axis. And I think that's because the canard was like at the edge of stalling, like one side was stalling first, and
Okay.
I think that's what's happening in there. So yeah.
Yep. It seemed like it handled the updrafts from the edges of the cliffs very well as well.
Oh yeah, that's the difficult one.
Yep.
Hmm. Yes. Yeah, and as Santiago was saying, yeah, in a conventional aircraft, you will always say, okay, your seat should be at the C quarters of your wing, right?
Yep.
Which wing in an Canard? So yeah.
So how did you discarded that general rule of thumb and just used actual equations to figure out the static margin instead?
Yeah,
Yeah.
and test a lot. Like moving, I don't know, the CG 5 millimeters to the back, 5 millimeters to the front, and
Okay.
test and see it. Yeah, yeah, it was pretty.
So how many tests did you do before you went off to the actual competition?
Actually, not that much. Yeah.
Like 2,
Nah,
Okay.
nah,
maybe 3.
nah. We did 4.
Okay.
Yeah, we did 4. Accounting for all the prototypes that we did before. So yeah.
Yep.
Yeah, but for holder was something also like that, like 3 or 4. It wasn't a lot too. Because basically what we were doing is like testing something. Okay, we need to change that. Okay, this change is not that easy, so we need to go back to the university and and work out some things. Yeah.
Yeah. So this is
However,
your manufacturing aspect now.
yes,
Oh,
yes,
sorry.
Santi.
Did you want to say something else, Mateo? Sorry.
No, it's okay. Santi?
No, it's okay. So yeah, we didn't 3D print the aircraft as a whole, but we did use 3D print a lot.
Yep.
For Dumbo, for example, the canard is almost fully 3D printed. The only part that isn't are the spars, which were special because, as you saw, the wings, the wing and the canard had to fall for the competition. So we used the carbon tube for the center and
Yep.
yeah, another like wooden strip, wooden piece of wood, yeah, for
Yep.
the other part that you could like put in and out, and that way you could like lock or unlock all the canards so they could fold. And the other parts of the main wing are also 3D printed. The ailerons are 3D printed, and the interface between the outer part of the main wing and the inner part, which is composite, are also 3D printed because we needed to have the hinge and also the tolerances because the 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 main wing all uses a system similar to the canard to fold the wing. We pull a piece of wood like from inside the carbon tube, and I think the for the main wheel are two carbon tubes. So you pull one outside from another, but the tolerances and the precision for the parts to mate and actually function like that and do it fast because you can't like be playing around with them in the middle of the competition because time was the time it took to do it was very important for the scoring. So it had to be fast. So the tolerances had to be very like precise and tight.
Yep.
Yeah, we use 3D printing for that. Um, Also for the motor mounts, the molds for the fuselage, because the fuselage is also composite, they are 3D printed. The leading edge of the main wing, of the middle section of the main wing, is also 3D printed, and the landing gears are 3D printed.
Okay. So in the legend here, the fuselage was carbon fiber and foam.
Yeah, we use I think maybe here we can see it better. We used 3D printed molds and then
Okay.
stitched some, what is it called, foam board? Yeah, a foam board between carbon fiber on the outside, and on the inside there is like a very light,
Fiberglass. Yep.
fiberglass, which is like
Yep.
20 grams per meter or something like that. I don't remember, but it's very light. So that was the sandwich that we built for the fuselage.
Yeah, basically what we said it was okay. The flight test, for example, aircrafts are great. I mean, you can hit them and they should be okay, right? Only
Yep.
it's a super hard landing. But we said basically okay, and which material they use? They use foam board, and if you can see the foam board is basically paper, the foam core, and paper, right?
Yep.
And we said, okay, let's try to do that. And we create our inertia of the fuselage. Obviously we used not paper, but composite materials. So that was our how we thought. Yeah, how we thought back in the day. Yeah.
Okay. So it seems like in terms of what parts were 3D printed compared to not 3D printed, the parts that were needed very tight tolerances, you went with 3D printing as opposed to the parts that didn't need to be 3D printed, you then went with a lighter material. Is that a correct generalization?
Correct. And also, we love 3D printing because we spent like a lot of time doing the aero design and then replicating that geometry into real life.
Yeah.
Kind of difficult.
Yep.
We don't have like a big CNC to CNC a big chunk of foam, or at the time we didn't have which we do now, a CNC foam coater that we're using now, but at the time we didn't. So the best way we had to really replicate the geometry in real life for the most important parts, which are the more sensitive parts, I would say.
Yeah.
Yep.
Parts of the wing. So yeah, we went for 3D printing for those parts. And
Yeah. So we care about of the leading edge mostly, right? And the other rigs, as Santiago said, yeah. And the rest, I mean, the flow is mostly detached after that. So we basically said, okay, we can use something cheaper.
but
right?
turbulent, yeah.
Yeah. So we can use like foam, simple foam.
Did your manufacturing approach change between Dumbo and Howler?
Yeah, a lot.
Yet.
3D printing with Dumbo. With Howler, we used much less because uh, for once, one of our team members, Pablo, which I will show later, he built a CNC foam cutter, like a hot wire foam cutter.
Yeah. Yeah.
We started using it for the main part of the wing because it was cheaper, faster, lighter. So yeah, it
Yep.
made sense. And also for the fuselage, I think we went for a wooden construction because of why I don't remember. Mateo.
Yeah, as we said, we wanted to decrease the drag, right? However, the molds that you use for the composites are not that cheap, right?
Yeah.
And as you are iterating during the aircraft design stage, you may have to do a lot of changes, right?
Yeah.
And maybe in the first prototype that you use, maybe you use molds for that carbon fiber fuselage. But for example, in the next prototype, maybe that molds don't work, right? Because you need to change the position of the wings or the wing attachment, whatever. So it was pretty expensive approach. So we basically said, okay, we can go a little cheaper on that, and maybe we can go with wood. It will be more heavy, yes. We can have the needed structure capabilities. So yeah, we went with that. And as you can see, however, we still use 3D printing stuff. For example, for the tail coupling method, and the main wing also. We have like a wing box for 3D printing, so we can be like sure if our incidence of the wing is how we want it to,
Yeah.
and not in another way. And for the nose mostly, yeah.
Yep. Okay.
Yeah, and the motor mounts.
And the movements, yeah.
So, what challenges did you encounter with manufacturing? It's going to be a lot, I understand.
Yeah, a lot of stuff. Mostly, when you're doing this project, you will encounter a lot of time delays, a lot.
Yeah.
Because your manufacturer team, they can say, okay, we can have this in 1 week. That's a lie. They will need 1 month approximately. So mostly time delays, yes, and for it's difficult because you need to be careful with the methods that you use, right? That's why we use a lot of them. We do not say like, okay, let's go only composites, let's go only 3D printing, let's go only foam. We use a lot because we think some of the parts will work better, right?
Yeah.
So yeah, that's why we use a lot of methods.
Yeah, for example, here you can see how our main spars are built. They are like an I-beam, but with the caps being carbon fiber. So we use a yeah, balsa wood or even plywood when needed, but it is heavier, so we usually use balsa wood and a couple of, like, I don't know how to call that, like sides of the wing spar of plywood, and that forms a channel where we can where we can lay the carbon fiber down, and that makes a very very strong wing. And the benefit of this is that we're not locked into the rigid geometry of the tubes of the carbon fiber tubes, because
Yeah.
if you want to have some dihedral, some polyhedral, some anneal,
Yeah.
whatever you want to have, or even if the wing has some taper, if it is too much, then the carbon tube would poke out of the surfaces because
Yeah.
yeah. So this allows us for having a continuous spar, and which is
Yeah.
like
So,
strong.
so on the continuous spar aspect, can you explain why having continuous spar is better for strength as opposed to having two spars that are cut in the middle and one for each side of the plane?
Yeah, because uh, when you're loading the wing, let's call that, like, we're not very concerned about the shear load, but the moment load, and it grows kind of exponentially towards the middle of the airplane, the middle of the wing.
Yeah.
So you for sure must have like the strongest part of the spar right in the middle of the wing.
Mm-hmm.
Yeah.
that for one part. For the other part, like any discontinuity you have, are you using like a coupler to join
Yep.
two spars together, or if the cross section of the spar changes suddenly, that's all like stress concentrators that would make the spar break at that point, at that specific point. So yeah, that's basically it.
Yeah, that's why you sometimes see some aircrafts like clap in the air
Yep.
because they exit like the load that they can handle, and you can almost always see where they break, and it's in the middle where
Yep.
the maximum bending moment concentrates. Yeah.
Yeah. I think there's a famous video on YouTube by a channel called XJet, I think, where a plane like a UAV literally breaks in midair and it's one wing just completely breaking off the entire fuselage, as you mentioned.
Yeah, it happens. Yeah.
Yeah. Something that I want to mention here in this slide is like the 3D print, because I'm a 3D print enthusiast, so I explode it as much as I can.
Yeah, me too.
Okay, great. So for important parts like that needed to be 3D printed, like the motor mounts and the couplers, like we mentioned, we also use this method, which is it's called a topology optimization, and also a narrative design, in which we design, well, depending on the goal of the part, but in this case, the ones that you can see, we design the shape of the part for the function, or for the main function it has, and the aerodynamic function, like on the one on the left, because yeah, it like tapers down from the motor goes here, um,
Yeah,
and then we run the optimization and use the topology that it found, the optimal topology to bear the loads that we are telling the software it has, to use
Yep.
as a modifier for the slicer program to 3D print it, so we can lay like the most material where it matters, and where it doesn't matter it's basically hollow or empty. So we use that to save weight on the 3D printed part, because one great con of the 3D printed parts is that they're kind of heavy usually.
Yep.
And so yeah, we use that for the motor mounts, for the couplers, and
Yeah.
yeah, for everything we could.
So, and then you put like a shell over the top, which is more aerodynamic.
Yeah, it prints like
Yep.
the skin. It prints the skin, and on the inside it prints
Yep.
the optimized topology.
No.
That's a smart idea.
Yeah, Santiago, also, if you could explain the outer wing from holder, that you see like some cross ribs. Yeah.
Okay, this yeah. So for Dumbo and for the outer wings of Howler, well, for one of the versions of Howler, we used like a fully 3D printed like part, and
Yep.
the way we like to do it is in vase mode, which I think I told you a little bit about it.
Yep. Well, maybe explain to everyone what vase mode is.
Okay, so when a 3D print is printing, it lays down a bit of the molten material. Then when it has to go to another part that it has to print, it retracts the filament, moves to the other part, de-retracts, and continue printing. But there is a mode called vase mode, which basically it takes the outer contour of the geometry you put in the slicer, and it just prints continuously without stopping, without retracting, um, and okay, what? Yeah, and
Yep.
that way you minimize. Well, one of the downsides of 3D printing is the how do you call that? Like,
The layer adhesion or what?
yeah, one is layer addition, yeah, but the other one is like the little imperfections and little voids and little
Yep.
nits and bits, and most of them happen in that process of retracting, moving, and de-retracting. Those are all tiny stress concentrations or stress concentrators.
Yep.
So using the base mode, for once, you avoid that. The other, well, you not completely avoid them, but you reduce them. Another point is the layer addition, well,
Adhesion.
addition, the layer addition,
Yep.
because um, since each layer is just being printed, like the outer wall, the outer contour, it does it much faster, and it goes to the next layer faster before the previous layer cools down. So the layer addition between layers, sorry, is much better also. And
Okay.
also it allows you to print with some foaming materials that have some agents like, I think it's like sodium bicarbonate most of the time, that
Okay.
it expands on the nozzle, it forms bubbles. It makes
Yep.
the material lighter,
Yep.
uh, but since they are expanding on the inside the nozzle, you don't have control of the material that is oozing out of the nozzle, so you cannot have a clean, like,
Yeah. A clean surface. Yeah.
yeah. So it would leave tons of stringing and ugly stuff and
Yeah.
voids if you try to print it the conventional way. And yeah, you gotta design. So you gotta design the geometry of the wing such that the the ribs that you're trying to form are part of the contour of the object that you're printing. And yeah, that's basically it.
That on that topic, to design the ribs as part of the entire contour, that's so that the vase mode can occur. Otherwise, if you have internal structures that the nozzle has to get to before it can go to the next layer, you'll have to retract to do that.
Yeah, exactly. You have to retract, and if it's a foaming filament, then all that foam would come out before
Yeah.
it reach the other part, and then when it tries to print again, then there will be a lack of material, and there will be a void of, yeah, in that part. Yeah, it would print pretty.
So speaking of roughness on the surface and imperfections, for your entire plane, not just the 3D printed parts, but also the different composites that you have, was the surface smooth enough straight out of the manufacturing process, or did you have to treat it somehow?
Actually, we didn't did anything about it because mostly our aero parts or the fuselage, we use like lighter fiberglass or carbon fiber, right? And that was actually a rough material. We didn't
Yep.
use anything mm, to do it smoothly. Yeah, right.
Okay.
Yeah,
Um,
something or
Did you?
something.
well, yeah, maybe I would say that we usually most of the parts, or most of the wing parts and tail parts, or well, the aerodynamic surface that were made in with foam, we covered with this very light fiberglass. Apart from the carbon fiber
Yep.
reinforcements, we had this like really light sheet of fiberglass on top. I think that would count as a kind of smoothing process maybe, but
Yeah.
yeah, no, not that much.
Yeah, for example, if you have used, for example, a monocoat, it's far more rough,
Yep.
right? Than these. I mean, these methods, these composite methods that we use, fiberglass, foam, and all of that, it's more rough than monocoat. That's the thing. I mean, I said monocoat because it's like a most commonly found, yeah, in this hobby, for example. Yeah.
Yep. So was the surface, do you think, smooth enough, or should it have needed some kind of lacquer or something to make it smoother overall, and then like a sanding?
Well, it's smoother is always better, but
Mm-hmm.
but the amount of work and the added weight wouldn't
Yep.
justify the gains.
Okay. Okay. In a way, though, maybe smoothness wasn't better in this case because it could trip the boundary layer and make it a bit more turbulent to delay stall a little bit in some of the crucial regions.
Yeah, exactly. That was
Maybe
fully.
Yep. maybe the canal that you're having stalling a little bit on landing for Dumbo would have probably stalled completely if it wasn't for the rough surface. Then, if it's right on the edge.
Yeah, that's true. Yeah.
Yeah, absolutely. Maybe.
So you also tested these parts for strength. The tail, at least, you were using different ways to hang off it. Were there a lot of breakages? And then how did you improve the strength from there?
No, for that one, for the one that we tested, it didn't break. We tested,
Okay.
yeah, it didn't break, and it was like two. I don't remember, 2 or 3 bottles. Where is that? Let me just check. Uh, no, no, here. Two.
Yeah.
Yeah, 2 bottles full of each shot.
Okay.
Mateo, do you remember how much is each bottle? How much? No, how? Yeah.
Oh, sure. I will say like, yeah, it's like 3 or 4 kilograms per bottle.
Okay. And you wanted to make your tail that strong to be able to support that because that's quite a high safety factor.
Yeah, exactly. Yes. Also, I mean, you can test it for a cross condition with a simple maneuver, I don't know, 60 degrees bank angle, but
Yeah.
you have to account for the phases that you mostly don't have control, right? There will be, I don't
Yeah.
know, I mean, wind gust, for example, or high G maneuver. You don't want your aircraft to break. That's why
Yep.
we went a little further. Yeah.
Okay. So in terms of, I don't know if you calculated it, but did you have an approximate safety factor based on the maneuvers that you did calculate?
Yeah. Well, for the parts that were 3D printed, yeah, because since we did the topology optimization, we also tested then a static test, like a static simulation.
Yep.
We usually, since, well, you know that 3D prints aren't isotropic at all, so we use like
Yep.
the weakest direction, which is D, for the input as material.
Yep.
And then we run the simulation. We usually do a 2 or 3 times safety factor, and
Okay.
after that we also 3D printed like in a more optimized angle than the worst angle possible. I mean, like, let's say I did the simulation so that the part could withstand the force, mm, being on the 3D printed Z-axis, but then I 3D printed it like at an angle, a 45 degrees
Yep.
angle or something like that. So it was actually stronger, added to the safety factor that was taken into account into the simulation. So the actual safety factor was larger,
Okay.
and I think like that's what it's for, to account for things that we don't account for, and 3D printing has a lot of those.
Yep.
But yeah,
Okay.
those we tested.
Okay. And then this year you're making another drone, is that it?
Well, yeah, we are making another one well, not actually us, Mateo and I are not participating this time.
Okay.
Some of the team members from the past competitions and some newer ones are going to Wichita this year to compete again with.
Yeah, it's actually like in 10 days or something like that. It's pretty close.
Oh, they're competing in 10 days.
Yeah, yeah, yeah.
Oh, wow. Okay. And what was the what are the requirements this year? What's the goal?
They are transporting ducks,
Okay.
like toy ducks, and they also have to release a banner. I mean, not release, but play with them. No. Yes, they need to release the banner and play with that. So they have a lot of challenges. They need to optimize also for flight time, because yeah, you have a lot of volume with the flight ducks. It is not that much about the weight, like
Okay.
the past competitions. But for example, for the mission for the banner, it is also a lot of drag that you have to account for.
Yep.
So yeah,
Okay.
it's pretty interesting competition for this year. Yeah.
And they use some of the, sorry, go ahead, Santiago.
No, go ahead. Sorry.
And they're using some of the lessons that you learned from last year and the equipment to make this new drone.
Yeah, for sure. Yeah. They use a lot of the methods that we develop, manufacturing methods, also the aircraft design methodology. I will say also how you manage the team with your times, with your task. Also some of the components that we use for past competitions,
Yeah.
they can
Yeah.
use it. So that saves a lot of time and
Yeah.
an effort to try to calculate which component to use. So yeah.
That last bit about using things that you used before, that dramatically reduces design time as well. Like you can just copy paste effectively.
Yeah, it's something like that. Yeah, it is the same, right? Because if you change something in your aircraft, it's basically different. It will behave different. So if you change, for example, the inertia, it will behave different. You won't have the same stability, and a lot of things. But yes, they could have like a better approach for a
Yep.
starting point this year. Yeah.
Yeah. Even like figuring out how to join pieces, that's a big
Sure.
thing, and having figured that out is a huge thing off your mind.
Exactly. Yeah, totally.
So we've been talking for 2 hours and we covered quite a lot. Is there anything else that you would like to talk about with these drones? Oh, really? Okay.
Well, first of all, I would like to share the video of the takeoff of Dumbo.
Yeah. Go ahead.
We haven't shown that.
This is for the actual competition now.
Yes.
Okay.
I think you can forward a bit. Yeah, there was the move.
Okay. Was that the shortest takeoff out of the entire competition?
For sure. For sure it was. It was actually difficult to maintain Dumbo in the ground while we were in the runway because it was windy also. So
Okay.
the canard wanted to lift already the aircraft without the motors on even. So the pilot needed to put the canard down
Yeah.
to create the downforce, right? And then it started the mission.
I'm guessing that the pilot got a little bit surprised by how quickly it took off.
Yeah. Everyone, I think in the video they say "whoa" or something like that.
Yeah. You have this up. Sorry. Yep.
To show this part because you saw that the Dumbo's fuselage was made of carbon fiber, and I think that, well, I personally think, I think Mateo agrees that was the cause of this problem that we had here, and we had also in previous flight with this airplane, is that the carbon fiber blocks the radio signal.
Okay.
For safety, they have us put like a
A fail-safe mode.
Yeah.
fail-safe mode on the airplane, which crosses the control inputs, like full aileron to the right, full rudder to the right, and full elevator down, I think, or up. I don't remember.
Yeah, it's basically crash your aircraft if you don't have control.
Yeah,
Yeah.
Okay. Oh, okay.
it makes crash the aircraft if it loses
Yeah.
signal. So here, it lost signal. I don't know if you can see it here. It will fall out of the sky. Here,
Yep.
For example,
there.
Yep.
yeah.
And then did the pilot just recover then,
Yes.
or did it? Okay.
Yeah,
Okay.
amazing for me. That's well, I want to say it now, but he's an amazing pilot. He was like, he came out of the blue, like, to help us. Yeah, he's amazing.
So your pilot came to the US as well to fly, or was it a pilot there as well, another one?
Yes. I mean, when we started the competition,
Yep.
we started like posting some things. Okay, this is the first time we are participating. A lot of that, I don't know. And he also he contacted us and he said,
Okay.
I want to help a Latin American team because he's also Ecuadorian. He's Ecuadorian. So he basically said, okay, I want to play for you. And we said, great, you have the experience, because he showed us that he fly a lot of acrobatics aircrafts, and he's great. And he also gives a lot of feedback that is actually great for us, because he said, for example, I need more aileron control, for example, or I need more elevator. So that's great. That's what you want for a test pilot. Mm-hmm.
Yeah. Just back on this, while you're talking, Santiago was showing this landing. Can you explain what happened at the landing? Because it like dramatically nosed up. Was that the pilot doing it, or was it something to do with the canards generating a lot of lift suddenly?
Probably.
The explanation is a little bit long because we had one airplane here, but we had to chop it up in pieces to take it to the States, rebuild it over again over there. So the airplane wasn't exactly the same that we tested in Colombia. So the CG wasn't the ideal CG wasn't
a little bit different. Yeah.
a little different. and because of that, the airplane was a little bit unstable. So on the first flight, it was like quite a bit unstable. This one was the most stable flight of them all, and I think that Joseph, which is the pilot, who is the pilot, um was trying like not to do anything that would stall the airplane at the last moment. So he was like just letting it slide like as easy as he could. Ah, sorry, I moved it. So yeah, there you see it. I think he's trying to not touch it, to just let it at the same descent
Yeah.
rate, and that's why it bounced like that. But as you can see, the landing gear, the forward landing gear did help.
Yeah.
So that was a bounce off the ground.
Yeah.
Yeah.
Okay.
It was- yeah.
Okay, I see. Yeah. Well, it still held up. The landing gear was strong enough.
Yes. Very important.
They are made with well, they are the core is PA6 carbon fiber, like it's a nylon.
Okay. Yeah.
We use it like yeah, literally like a core. Like, have you ever seen like this what's the name of that aramid? No, the honeycomb.
Yeah, I understand. Yeah.
Yeah, okay. We try to recreate that, but with the 3D printing, because yeah, the actual honeycomb is like quite expensive and quite difficult to work with. You need a CNC to basically shape it.
Yeah.
So we 3D printed the core, and then we wrapped it in carbon fiber, so it gets you the sandwich composite that it's really strong. And the good point of that methodology is that you can design and make a different landing gear every time you want. You're not stuck to molds, which was the previous method that we were using. So yeah, that was and this one is the other plane, Howler, in one of the missions. I don't know if this one is the one that crashes it. No.
I don't remember. The thing with Holder is basically we ran out of battery in the final lap. So our pilot crosses the line, we finish the mission. However, for the mission to account, you have to land.
Okay.
Of course. So we ran out of battery and he couldn't land properly.
Okay.
I think this is the video.
Maybe.
Yeah, it is.
Yeah.
What kind of wind is that on the day? Because it seems to be quite a strong wind.
Yeah, like a lot.
Yeah, actually,
Yeah.
in Wichita was higher, I will say.
Yep.
In Tucson, this was in Tucson, Arizona.
Yep. Okay.
And it was pretty hot also.
And so the higher wing loading helped you then cut through the air a little bit then.
Yes, yeah.
But the wind also was like what?
Yeah. You can see it's getting taken when it goes with the wind very quickly.
Yeah. So
Okay.
I will move it forward.
Yeah, basically, this aircraft was great in stability and handling quality. The pilot said that it doesn't need anything else, so it was great. It was
Yeah.
great. The thing was the mission that we crashed. It was pretty heavy. It was the 15 kilos. So there we finished the mission. However, there we ran out of battery,
Okay.
and the aircraft couldn't recover that. So,
Okay.
yeah.
Well, how much damage was there to the plane?
Oh, I think yeah.
Okay.
So yeah, basically our nose was completely destroyed. The nozzle gear too. The motor mounts also couldn't hold
Yeah.
that the crash. But yeah,
I think they were mechanical fuses because the motors were fine in the end.
yeah,
Okay.
But I want to talk to a little bit about because you can see it here like a little bit better of the coupling mechanisms of the outer
Yeah.
wing and the inner wing. You can see those little holes. Can you see my pointer?
Yeah, I can see.
So those little holes, we're using here a IKEA mechanism.
Okay.
How are those called?
no, I don't know.
You use dowels to put in there, like little sticks. Yeah, dowels. Yep.
yeah,
Yeah.
And it pulls it tight against the other part, and
Yep.
yeah, it works perfectly. I really
Yeah.
like it. I really like that.
Yeah,
How did the dowel stay in there without falling out? Just through friction?
No, the pins that are in here and in the other wing are glued to the wing.
Yep.
And here in the holes are the nuts that turn. They have a turn to pull the dowel.
Yep. Oh, okay.
Yeah. Let me see if I. Oh, okay. And we're going to the end.
yeah. This is the team throughout the years.
Yep.
Yeah. So
The-
in the left side we have the Dumbo competition, and the right side we have the holder competition.
Before and after.
Yes.
Yeah,
Yeah. 2024 and 2025. That's
Okay.
some new members, some other members. Yeah.
Yeah, I wanted to display them all because we're both talking here, but like it's a team effort and everyone
Yep.
like did their part. So I just wanted to show them here
Sure.
to all of them. So yeah, that's the team.
So the team was about 15 people or so. This was the
Yeah.
Dumbo team or the Howard
This is
team?
the holder. Yeah.
Okay.
Yeah. The research group is pretty new, right? When we joined our undergraduate program, they didn't even have something about aeronautics. So we
Okay.
were the first ones to create the group, to start testing, to start building. So yeah, it has been building up. For the first competition, we were only 6 people traveling to the USA to the competition. The next year, we were 10 people. And I think this year they recommend like 13 or 12 people.
Okay.
So yeah, it's been increasing.
Well, you had a lot of success. You did a good job.
Yeah, I think we did good. Yeah.
Yeah. So, two things. First of all, the videos that you showed about both planes, you have them on your YouTube, on your YouTube channel, is it?
Yeah, both are on my YouTube channel.
Yeah. Do you know what that's called by memory? I'll link it below as well if you send me the link. That way, if anyone wants to.
A random number. I don't know.
Yeah. And then if people watching this want to contact you or get in touch, how can they do that best?
Okay, so our research group, it's called ICARUS, right? And this is our web page, so you can go there, see what we have. We actually have some 3D models of our aircraft if you want to play with them.
Okay.
And this is our Instagram too, udea _ aeronautics. We have a lot of stuff there too. If you want to contact us, there is our Gmail, and for us, there you have our LinkedIn accounts.
Okay.
Yep.
Yeah. Well, thank you so much. Yeah. Is there anything else that you wanted to say?
No, thank you for the space. It's great.
Thank you for coming on and showing your projects. They were really interesting, and I think for me the ingenuity and the big difference between the first and second time was major. It's really common when you do one thing, you do something similar the next time as opposed to have something radically different to do. So it's interesting
Yeah.
to see the big change in your design.
Great. Thank you very much.
Thank you very much.
For having us. It was amazing. Yeah.
You too.
Yeah.